Okay, good morning, everyone. My name is Febria. I'm the curriculum manager for Bangkit for this year. Thank you so much for your time. Today we will have sessions with Laurence Moroney. He is AI lead at Google. He is leading TensorFlow. And let me add him to the stage. Hi, Laurence. How are you?
Hello, I'm doing well. How are you?
I'm great. I'm great. Thank you so much for your time, for
Oh,
sharing
thank
with
you.
our students. Uh, Without further ado, I think I will leave the stage to you. Let me quickly add your presentations. Okay, enjoy,
Sounds
everyone.
good. Thank you, February, and thank you, everybody, and welcome to this version of the Bangkit Academy. And we did one last year, and it was incredibly successful. And some people went on to do amazing things, and I'm really excited to see and to hear what everybody in this group will do. So, as February mentioned, I'm Laurence. I lead TensorFlow advocacy at Google. I'm based in Seattle, so it's 8 p.m. for me. Good morning to you. Good evening to me. And tonight, I just want to talk a little bit about TensorFlow, about some of the reasons behind why we do TensorFlow. And for those of you who may be new to machine learning, and in particular programming machine learning, and how that will work, I'm going to give a little bit of an overview of that. I believe you'll be learning from my Coursera content or maybe from my books, and some of this will look familiar if you've done that before. So first of all, I just want to talk about the economic opportunity that comes with TensorFlow. I drew this chart a few months ago based on economic activity of several nations, mostly Western European, United States, Canada, and stuff like that. And this has been the GDP of these countries since about the mid-1950s. And as you can imagine, there's that big drop on the right, and that was in 2020 because of the COVID pandemic and how it impacted them. But all economists will say that despite that, we still see an overall increase. And we can see that economies are growing, opportunities are growing, and why should we bother getting involved in something like AI or something like programming or anything like that if the economy and the opportunities are going to grow anyway? And I think that's a great question. But if we dig a little bit deeper into this chart and we look at an analytic around this chart, hopefully that will help answer the question. So this is an analytic that I drew based on the previous chart, where instead of plotting the GDP on each particular year, I did the GDP as a function of the previous 4 years. So in the case of where the GDP is at about 1, that means growth was flat in that particular year. Obviously, if it's above 1, it's doing well. If it's below 1, it's not doing so well. And as a result, when I look at these, at this period of time, I could see what was happening is you can see there's 2 plateaus here. There's this one and there's this one. But I didn't put dates on this map, and I did that for a reason, because I wanted to discuss these plateaus. So this first plateau started around, I'm trying to remember now exactly, I think it started around 1991, and it lasted until about 2007. And what this plateau is, of course, is the web economy. So with the introduction of the browser and with the introduction of the web server and with people, inventing whole new industries and whole new businesses, Google didn't exist without this. Microsoft basically didn't exist without this. Facebook, many of these companies didn't exist without this and wouldn't exist without this revolution. But the introduction of the web and the introduction of the web as a viable platform for people to build applications on drove this massive sustained period of growth. And as a result, we have a whole new economy. The most valuable companies in the world, the Apples, the Microsofts, the Teslas, the Googles, the Facebooks, all of these companies came out of this revolution. And I think it's worth pointing out how big a revolution that was. That was the first great revolution of my career, where people really needed to pivot away from how they had done things previously to think about the new paradigm. Prior to this, you would build applications that might get distributed on a CD and get installed on somebody's desktop, and you didn't have that kind of scale. During this revolution, you changed the way you built applications because you built for scale, you built with a server client architecture, and you thought about the web, you built for the browser, you built for distributed systems and all that kind of thing. And as a result, there's massive time of economic this massive time of economic boom. And as a result, as I've mentioned, many great companies came out of it. The second one then began in around 2007 and was showing great signs of climbing before, of course, in 2020 when COVID hit. And this is the mobile economy. And, remember also that this is relative to the previous chart. So even though this looks smaller than the peak on the left, in some ways it's actually bigger because this is what it was like relative to that one, how much it has grown on top of that one. But the point again here is that the overall average was growing, moving upwards during this period of time. And you can say this period of time began with the advent of the smartphone and the smartphone economy. I read a statistic a few weeks ago that in the UK alone, there are 600,000 people employed in the Apple App Store ecosystem, in various capacities. And as a result, in a workforce, I believe, of about 30 million, 600,000 because of one app store is very significant. And this app economy has again driven new businesses, new things that you previously wouldn't have heard of, things like an Instagram before a mobile phone, who needed it? I mean, you would take photos with your camera, and it was hard to share. Businesses like Uber, delivery businesses, all of those kind of things that came about because of the app economy was that second great revolution. Obviously, the big drop on the right is because of COVID and the COVID pandemic. But I believe we're at the beginning of the next great revolution, which is the AI revolution. And I think this will be bigger than both of these, not just from a dollar perspective, but also from the amount of jobs that will be created as a result of AI. And like I said, I've seen these two paradigm shifts already in my career. I think we're beginning the third paradigm shift. And I think the key to that is going to be, more than anything, is going to be software developers. The web would not have happened the way that it did without millions of developers building innovative applications. The mobile app ecosystem, same thing, without millions of developers building those applications that, grew huge companies like Uber from zero, or Instagram, or any of the other app economy, and any of the other big apps that you see out there. And then if we look at things like the World Economic Forum, they did a Jobs of Tomorrow report. It's at this link. And if you take a look at it, where they were looking at, the future growth in jobs, the biggest was data and AI, where they expect 37% increase in jobs. Not far behind that is cloud computing. And we know how much of an investment has been in cloud computing. I used to work for Microsoft, and if you look at Microsoft's stock, I think it has increased about 10x in the last few years because of their pivot towards Windows Azure and cloud computing. So cloud computing is a very bright and very affluent future. But despite that, the job growth in data and AI is actually bigger at about 37% growth instead of 34. 34, of course, is really healthy. But this is just showing, according to the World Economic Forum, the jobs of tomorrow, you can see, are in that space. And then similarly, the Forbes report, which you can see at this link, is talking about the global ML market, increasing at a compound annual growth rate of over 40% per year between 2017 and 2024. And all of software revenue, same kind of thing, 43% growth between 2018 and 2025. So we can see, as a software developer, and particularly as an AI or ML software developer, the opportunities there are huge. And the amount of growth that we're seeing, $20 billion business in ML by 2024, 126 billion in overall AI software, the growth potential is, as you can see, is phenomenal. And when it comes to learning this, actually, also, if I go back to the World Economic Forum, they actually cite the TensorFlow Coursera course, which I teach, which will be part of what you're doing in this academy, as one of the key skills in the jobs of tomorrow. So you're doing the right thing and you're in the right place. Okay, so I've talked a lot about the potential behind AI and the opportunities that are going to be out there. And by investing in your skills in AI now, those are the opportunities that are going to be available to you. But there's lots of different AI frameworks. TensorFlow is just one of them. And I'm not going to pretend that all of that opportunity and all of that growth will be as a result of TensorFlow. But we do believe that TensorFlow is, an incredibly important framework that will help drive this. And some solutions that have already been built with TensorFlow are things like, on the top left here, you can see a scan. And we've been able to work with a lot of researchers who do eye scans, who do lung scans, who do other kinds of MRIs to build state-of-the-art diagnosis systems that are helping doctors diagnose and be more efficient in their work. Now, one of the things that people always ask is, hey, will this replace doctors? And I would argue that it will not. What it is doing and what we've seen AI and ML being able to do is allow doctors to be more effective. So if they are quicker at doing their job, then they can see more patients and they can help more people. India, as a country, has the highest rate of diabetic retinopathy in the world, but it has a massive shortage of qualified ophthalmologists. And with that in mind, we worked with some folks in India to build a diabetic retinopathy detector. You've probably heard about it. It's quite famous. With the idea being that the scarcity of doctors won't impact the spread of the disease. By the fact that the doctors are able to scale better, they're able to treat the disease better, and the disease is easily treatable if it's detected early. But there weren't enough doctors to detect it with everybody early. And as a result, it's a great place where AI has been able to help out. On the top right, you can see cassava farmers in Tanzania. And this is one of my favorite projects. The goal of this project was that these farmers will grow cash crops that they sell in the market to be able to feed their family, send their kids to school, and all of these kind of things. Occasionally, cash crops fail. And as the cash crop fails, there would be famine, there would be starvation, there would be death. So a lot of farmers grow a backup crop called, and cassava is a very effective backup crop. So if that cash crop fails, they're not going to starve. They'll still have cassava. If, like any good engineer, if your backup fails, you're in trouble. So one of the things about cassava is that blight will spread very quickly in cassava plants, and it's not easily detectable. And when you do detect it, not only the plants that you detected on, but most of the other plants in the field are actually already impacted by the blight, and you've lost potentially your entire crop. So, but blight, a little bit like diabetic retinopathy, with early detection, will allow you to be able to treat it, will allow you to be able to destroy that plant and maybe a few around it without losing your entire crop. So some researchers and some folks in Tanzania built an app that runs on a mobile phone and allows the farmer to take a photograph of a leaf and to determine if that leaf is blighted or not. And as a result, they can do the same kind of early detection and prevention. So there's lots of projects like this around the world. All of these are powered by TensorFlow. And one of the most important parts of TensorFlow is the fact that it's deployable in a number of different platforms. Like in the case of the cassava farmer here, it was on a mobile phone. And so if you're a TensorFlow developer, you can deploy to phones, you can deploy to the web. You have a version that runs in JavaScript that you can deploy to the browser. And increasingly more common now is being able to deploy to microcontrollers and embedded systems. So these skills will allow you to take your work and deploy it to any of these and maybe build the next great solution like the diabetic retinopathy or the cassava. So to talk a little bit about the ecosystem, we've had about 200 million downloads of TensorFlow in the 5 years since we released it, or 5.5 years since we released it. My team, we do advocacy around it. So we do the tutorials, the guides, the blogs, YouTube, all of that kind of thing. And as you can see, the numbers here have been growing really sharply. And the one that I'm particularly excited about are the people who are learning on open online courses, who are getting hands-on, who are coding, who are developing. And we're approaching 1 million learners. So as a result, thinking about the economic impact that I was talking about earlier, the web or the mobile wouldn't have happened without enough developers building innovative applications to drive us all forward. And as a result, my personal mission and what I've been working on is to really drive as much education, as much awareness, and as much hands-on skills in AI and ML as possible. And as a result, we're approaching 1 million learners on our open courses. And there's an interesting statistic here. When I first started working on the TensorFlow platform, I took on a challenge. And I learned at that time that in the world, there were 300,000 AI practitioners. There were about 100,000 in China, about 100,000 in the US, and about 100,000 in the rest of the world. And that figure was measured by the only way they could, and that was by the number of people who had their name on a research paper. So that told me that, if nothing else, that AI was very much research oriented and not application deployment developer oriented. Now, there's lots of different measurements for how many developers there are in the world. I'm going to go by a rule of thumb saying there were about 30 million software developers in the world. So if we could train 10% of the world's software developers, that would be 3 million. And we would increase the number of AI practitioners in the world by tenfold. And that has been our mission at Google, is to try and drive that next great revolution I've been talking about by empowering developers, by open sourcing the platform, reducing any barrier of entry. You don't have to buy anything, by providing as much training as possible, by providing inspiration and information on things like blogs and YouTube. And of course, by trying to give you a platform on which you can develop if you don't have a development box and you don't have a GPU or anything like that, through something called Google Colab, which allows you to build machine learning models in the browser using powerful backends like GPUs and TPUs without you needing to install anything. So that's really been our mission, and that's what we're working hard to drive forward. So to talk a little bit about the ecosystem, when you hear about machine learning and AI, typically you're going to hear about training. And training is the process of creating a model. And once you have that model, you use that model in a process called inference. We'll talk about that a little bit later. But the goal behind TensorFlow is to have a full ecosystem of tools that will allow you to do training. And on this here, there's the word Keras that you probably see it right about here. Oh, sorry, you don't see that mouse. Right about here, you see Keras. And the idea behind Keras is we wanted to have a framework that was very easy to use for beginners or for people who are building basic models, but is also usable by researchers who are on the cutting edge. So whatever they build on the cutting edge will work its way back to the rest of us as developers. So we've been investing really, really heavily in that to make sure that that meets both of those aims. And then another thing that's really important that you'll learn as you go along your journey is this thing called distribution strategy. If you're not a machine learning person and you haven't done a lot of it, you've probably heard anecdotes about how long it can take an AI to learn how to do something or be trained how to do something. And certainly with better algorithms or more powerful machines, that's getting faster. But giant models that can take hours or days to train, it's still not very efficient for you to have to set it off for training and come back in a couple of days. So the goal behind distribution strategy, again, we've invested heavily in TensorFlow, is to allow you to split that training across multiple cores. So instead of one machine doing all the training, you could have potentially hundreds of machines, and being able to split your training across those and then being able to aggregate that effectively is the goal behind distribution strategy. You'll see we've done a lot of investment in that. And then over on the right-hand side is what I was talking about earlier on, where you can deploy your models. And in some ways, to me, that's the distinguishing factor, is what makes TensorFlow, I think, the primary machine learning framework, because of the number of places where you can place your model. People might argue that other frameworks are quicker or more intuitive, and that I think that's very subjective. But what is not subjective is the fact that with TensorFlow alone, you can create models. You can deploy them on premises with serving. You can deploy them to mobile phones or embedded systems with Light. And you can deploy them to the browser or to something like a Node.js backend with TensorFlow.js. And I'm going to give a little demo actually of one model, and it's built into Google Slides. So I'm going to turn it on now, and let's see. There we go. Now let's see, it actually recognizes my voice. So as I'm speaking, it's actually creating these automatic captions. So this is a TensorFlow model. This TensorFlow model is running using the TensorFlow serving that I show on the top right here. And as I am speaking, it is streaming my voice up to that server. It is getting an inference back from that server, and that inference will be the the speech to text of my words, which it then updates the screen with. And this model was actually trained on a number of different voices, so it can recognize multiple voices. I have a very strange accent where I grew up between Ireland and Wales and England and the United States. And so I don't have any particular accent, but as you can see, it actually recognizes my voice really well. And one joke I always like to tell is the second longest word in the English language is, anybody know it? Okay, the second longest word in the English language is anti-disestablishmentarianism. And if you may notice, it actually finishes the word before I do. Because at some point, when I'm saying those syllables, there's only one word that will complete it, and the computer actually can complete the word, despite the round trip to the server, quicker than I do. So if I say it again, watch very closely. Anti-disestablishment, it actually finished it there before I could. So this is like a really nice application of AI, is a really nice application of the TensorFlow model. Okay, so I've been talking about the ecosystem of TensorFlow. We've been growing it for the last couple of years, and we're on 2.4 right now. And the goal of the history of TensorFlow is when we released version 1.x, it was really aimed at researchers. It was aimed at cutting edge. With the release of TensorFlow 2.0 is when we really wanted to pivot towards developers. We really wanted to pivot towards the 30 million and not the 300,000. So we've been doing things like eager execution by default, and that means your TensorFlow code runs like any other Python code. So you got step-by-step debugging, inspection of variables, and stuff like that. And it also has the tight integration with Keras, and Keras, the framework that I was telling you about earlier on. As we've evolved it, we've also been building in performance improvements, distribution strategy, and all of the kind of things that I was talking about. And the latest version of TensorFlow is 2.4, as you can see here. I'm not going to go into a whole lot of detail on this one, but one of the things I just want to call out is the investment in quality and performance. So if you are building larger models, if you're graduating on from learning and you're working in an environment where you're dealing with a lot of data and you want to do distributed training, we've been investing very heavily in that. Okay, so switching gears now for a moment, I want to talk a little bit about what does your journey as a developer look like when you are using TensorFlow or when you're doing machine learning. Now, typically, if you are writing code, your job as a coder is always you define the rules that will determine the behavior of a program. And everything that it does is kind of predetermined by you as a developer. So for example, a breakout game like the one that you see here, you have to code for all the different scenarios, right? So what happens when the ball hits a brick? You write a rule, something along the lines of the code here, like if the ball collides with the brick, remove the brick, change the direction of the ball. You have to write the code that places the bricks on the screen, moves the bat according to the user's input, moves the ball according to a timer. And all of these things are rules that you're actually coding. And you have to think about all of these in advance, pre-calculate, predetermine all of these, and write the code to be able to do it. So, of course, the more complex the program gets, the more code you have to write. And sooner or later, some scenarios can be infeasible for you to write the code. It's just the value that you would get back from writing thousands or hundreds of thousands of lines of code just may not be worth it. So that's the traditional programming paradigm. I always like to draw it in a box like this one. You have rules in, you have data in, and you have answers out. The rules you're expressing in code, the data is available to you in the app, and when you write this, you're going to get answers out of it. So for example, in the breakout game, the data will be the location of the brick, the location of the ball, and the rule you would apply is, hey, if they're in the same place, you want to remove the brick and change the direction of the ball, and that's the answers that you're getting out for the next part of the loop so that the game can continue. So that's traditional programming, and that's what traditional programming looks like and has always looked like. But then consider, I was talking about sometimes writing code can lead to infeasible things, and it's just not worth you writing all the code that you would have to write. So consider something like activity detection. So a lot of us now wear like smartwatches, and those smartwatches help us with our fitness, but for them to be able to do that, they also need to be able to detect our activity. So consider if you wanted to build something like that, how would you do it writing code? So take, for example, we want to detect if the person is walking. Well, we could go by the speed. Maybe there's data on the device that gives us the speed using GPS or something like that. And we could say, well, if the speed is lower than a certain amount, we can pretty much guess that they're walking. They're probably walking. Simple algorithm. Then we say, okay, what if we want them to be running? Then we could say, well, if the speed's less than that amount, we could say they're walking. Otherwise, we can say that they're running. We still have a crude algorithm. It kind of sort of works. What if they're biking? Then we can still use a similar algorithm, like if it's less than 4, they're probably walking. If it's less than 12, they're probably running. Otherwise, they're biking. We go, again, it's a naive algorithm, but it kind of sort of works. What happens if they're golfing? How do we detect that? How do we determine that? We just can't. The amount of lines of code that would have to write for determining they're stationary, they hit the ball, they walk a bit, they stop, the movement of their arms, the movement of their wrists, these kind of things, it would take maybe thousands and thousands of lines of code to be able to do this. We're not even sure if it would work. It would be a massive investment, and the payback is we detect that they play golf. And it may not be feasible for us to do that. And also for the other activity detection, it's somewhat naive because we might walk downhill faster than we run uphill, or different people walk and run at different speeds. So as a result, the amount of code that we'd have to write to do something like this, it just becomes infeasible. Now, I don't think it's a coincidence by the fact that we now have smartwatches like this one that can do this right around the same time as we have AI algorithms and machine learning algorithms, that they've opened up new scenarios where we can start building apps like this. And they'll work in this way. So here's the traditional programming paradigm that I spoke about earlier: rules and data in, answers out. Machine learning, we're just going to flip that around. We're just going to say, instead of rules and data in and answers out, let's put answers and data in and have the computer infer what the rules are. Now that probably seems a little bit abstract, so let me show that with the example again. So we can imagine now, what if we, instead of trying to figure out what, like, the rules for somebody walking, running, biking, or golfing, what if we gather lots of data of lots of different people doing these activities, and then from that data, we tell a computer that this piece of data is a person walking, this piece of data is one running, this is biking, and this is golfing, and have a computer figure out the patterns. So maybe, for example, if a computer sees this pattern always when somebody's walking, no matter who they are, we could then establish a rule that, well, when you see this data, that person's walking. Now, a computer can see patterns that a human can't see. You know, it doesn't have to express it in rules like if this, then that. It could just say, hey, this data is always there, or almost always there when the person is walking. So we can establish that when you see that data, the person's walking. And if we see this piece of data, they're running, this one they're biking, and this one they're golfing. So that elaborate pattern matching is the basis of machine learning. So instead of us trying to write code ourselves to determine the activity of a person, what if we did something like this? We gave the computer lots and lots of data. We had the computer and we labeled that data by saying this is walking, running, biking, or golfing. Had a computer figure out what makes each one each based solely on the data and no other knowledge. Then we could say we have trained a model, and that model can recognize activities. So the process of how a computer does that is actually quite simple. First thing it's going to do, it's going to make a guess. It's going to make a guess that, hey, this piece of data for walking, this piece for biking, this piece for running, and all of those kind of things. Totally rough guess. If there's 4 activities like I had in the previous diagram, you'd expect it to get it right quarter of the time. So it's going to make that guess, and then it's going to measure that accuracy. So it'll say, well, there's 4 different ones. We'd expect our guess to be right 1 in 4 times, so about 25% of the time. And then it will say, okay, now I have the guess, now I have the accuracy. Can I optimize my guess? Can I learn from the accuracy of my guess to make my guess better? And then that's the next step, you repeat. So the training process is continually repeating this, getting all your data, trying to match them, make a guess, measure the accuracy of that guess, optimize that guess, and continue and repeat. And that's what machine learning actually is. That's all it is. So if I go back to this paradigm and machine learning, and I say it's like labels and data in, earlier I was calling it answers and data. In machine learning, you'll hear the term labels, and that just means, like in the example that I showed earlier, the label is walking, right, running, biking, those kind of things. And the data is whatever data was gathered from the user, from whatever device that they were wearing at the time. And from that, we'll infer the rules. And the rules are effectively, well, if you see this bit of data, they're probably walking. If you see this bit of data, they're probably running, instead of us trying to think in terms of speed. So that's the concept machine learning, where a machine will learn how to match those patterns. That will create a model. And then at runtime, when you provide that model to people, and remember earlier I was talking about TensorFlow having different deployment options like the web, the browser, the mobile device, embedded systems. That's where your model goes. And then at runtime, that model, you give it the data and it will give you back an inference, an answer about what it thinks that data is. So you might be putting this onto a smartwatch, for example, and the person starts running. It sees the data that kind of looks like running, and it will give you an inference back to say, I think you are running. Or more accurately, maybe when you stop running, you want it to stop logging you as running. So it'd say, hey, I think you've stopped running and now you're walking. And again, from the data that's gathered using that model, that's giving you those inferences. So that's a lot of theory. So let me explain this in code. And most of what I like to teach is really talking about doing things in code. And you'll see we'll do it mostly in Python. So if you don't know Python already, it's a really useful language to learn. Unfortunately, it's a very easy language to learn. So I'm going to show two sets of numbers here. And there's a relationship between these numbers. There's a pattern that gives you the y for the x, right? If y is the answer and x is the data, there is a rule that gives you whatever y is from x. So think about that for a second, and can you see what the rule is? So normally people will like look at this and they'll go, well, I see when x is 0, y is -1. So y is probably a multiple of x minus 1. And it's like, okay. Then I look at the 1 and I see y is 1. So what multiple of x minus 1 will give you 1? Well, that would be 2x minus 1. And then I look at the 2, 2x minus 1 will give me 3. That's correct. I look at the 3, 2x minus 1 will give me 5. That's correct. Okay, I think I figured out the rule. I've made a guess. I've measured my accuracy. And in this case, my guess was correct. And because my accuracy here was 100%, because every time I plug the x into y equals 2x minus 1, I get the correct y. And that's exactly what a computer is going to do, but it's probably not going to be as smart as you are doing it. It's going to take a few extra turns. So here's the code on how you would train a machine to learn the relationship between these two sets of values using TensorFlow and using the Keras I was talking about earlier on. So this first line is the simplest possible neural network. You've probably seen neural networks. We got lots of layers with circles in them, and those circles are all connected with each other. And those circles are often called neurons, and they're densely connected to each other because everyone in every layer is connected to everyone in the next layer and the previous layer. And so I'd say, well, the simplest possible neural network is there's one layer and there's one neuron in that one layer. And that's what this line of code is saying. So the keras.layers.dense that you see here, that's saying this is a dense neural network of that. So it means it's that type. Units equals 1 means there's one neuron. And by the fact that I only make one declaration to dense, that means there's only one layer. So this is one layer with one neuron in it. A very simple neural network. So again, remembering the algorithm I was talking about earlier on, you make a guess, you measure your accuracy, and you optimize your guess. So the next line you can see here was model.compile, and it says optimizer equals SGD and loss equals mean squared error. Well, the loss function in machine learning, its job is to measure your accuracy. So when you've made a guess, it's going to look at the state of the neurons in the neural network. It's going to test how the neural network did against the data, and it's going to measure how good or how bad that guess was. So say, take, for example, a random guess that says, hey, y equals 5x plus 5. Then it would say, okay, I'll look at my accuracy, and if y equals 5x plus 5, then when x equals 0, I would expect y to be 5. But y is actually -1. So my accuracy is way off, right? So that's what the loss function is going to do. And in this case, the loss function is a mean squared error. Now, if you have any exposure to machine learning before this, you've probably seen lots of math, lots of calculus, and this is where the heavy duty math is taking place in the loss function and in the optimizer that we'll show in a moment. But as a coder, one of the things that I'm most excited about is the fact that TensorFlow provides many, many state-of-the-art loss functions and optimizers, as well as the ability to create your own if you want. But you don't need to be a mathematician to be able to use it. You can just pick your loss function. The fun then becomes picking which loss function, which optimizer, and how do you tune those. And that's where you really want to spend some time learning TensorFlow and doing a lot of trial and error. So in this case, I've picked the mean squared error loss function for you. And that's this part of the algorithm is saying to make a guess, measure your accuracy, optimize your guess, and the loss function is doing that. As the name suggests, the optimize your guess is what the optimizer does. Now in this case, its mysterious name, SGD, that stands for stochastic gradient descent. And again, this is the heavy duty calculus that you've probably seen if you've been doing any kind of learning of machine learning. And all that is doing is its job is to minimize the loss. So whatever lack of accuracy that you get, its job is to reduce that as much as possible. You may see there's a curve, like a U-shaped curve, and the image of a ball on the curve. And the bottom of the curve is loss 0. So if you try to move the ball down the curve to the bottom of the curve, you're reducing your loss. And the optimizer is its job to do that, to figure out the math of that curve and how to move down that curve. Fortunately, to get started and to be able to get up and running with building models, you don't need to understand that math. You just pick an optimizer. And that's what we're doing here. We're just saying we've defined our model as a single layer with a single neuron. And then we're going to say it's going to be optimized by SGD, and its loss function is going to be mean squared error. Then the next line is just, hey, this is your data, your x's and your y's, this np.array. If you're not familiar with Python, there's a very popular add-on to Python called NumPy that allows you to do a lot of math stuff, and the array type in NumPy is really useful in TensorFlow. So here we're just saying, here's my input data, here's my output data, and I'm defining them as NP arrays. And then the process of making a guess, measuring your accuracy, optimizing your guess is really fitting the input data to the output data to try to figure out the rule that determines how do you get that output data or that y value from that input data or that x value. So you're going to make a guess, you're going to measure your accuracy, you're going to optimize, you're going to repeat. And you see here it says epochs equals 500. That's the number of times it's repeating. So after 500 times around this algorithm, it actually takes a lot less, but say after 500 times around this algorithm, you're going to have a model that's very, very good at determining the relationship between these x's and these y's. So if I were to then test that model by issuing what's called a prediction to get an inference, then I say, well, model.predict 10, what answer do you think it would give if it has learned y equals 2x minus 1? Now, initially, you'd probably think 19, and you would actually be wrong because it's going to give you a value that's very, very close to 19, but not 19 exactly. And the reason for this, again, it's trying to learn the relationship between these two pieces of data. It has no idea what that relationship is. It's trying to learn them. And it will give you back that there's a very high probability that these are on a straight line. But there's only 6 points. After these 6 points, there's a chance that the line may diverge and may no longer be a straight line. And as a result, as the neural network is learning, you're going to get that slight bit of like accuracy loss. In this case, you and I can see it's a straight line. The computer can see these 6 points are a straight line, but there's no guarantee that when x equals 10, y is on the same line. But there's a very high probability that it is. And as a result, that's factored in, and you'll probably get an answer like 18.998 or something along those lines. And that's an important thing to remember when you're dealing with neural networks, when you're dealing with AI, is that it tends to deal in probabilities. You show it a picture of a cat, it's not going to tell you that's a picture of a cat. It's going to tell you there's a 99% chance you're looking at a cat. You show it a picture of a cassava leaf, same thing. It might tell you there's a 70% chance that this is diseased. Those type of things. So always remember you're going to be dealing in probabilities. And that's why I was saying the model.predict, you're going to get that. So that brings us to the end of what I wanted to talk about tonight. So just to go over the opportunities in AI, go over what TensorFlow is, talk a little bit about the TensorFlow ecosystem, and then give you a brief coding example so you can see how easy it is for you to code a very simple neural network like this one, but even more complex ones like computer vision or natural language processing or sequence modeling are all, I won't say very easy to do, but we've certainly designed to make them a lot easier for you to do in Python style language. So with that, I can wrap up there, and Febria, I can take any questions.
Sure. Thank you, Lawrence. It's really cool to see the automatic captioning features.
Oh, thank you. I'll turn it back on. Yeah, just let me turn it back on. Yes. It does sometimes get it wrong, though. I think it said your name was February.
Oh, yeah.
Febria.
Okay. Yeah. I think we have some questions from our Discord. Let me just quickly share this. The first question is from Kevin Cristianto. I heard that you have been doing machine learning even before Python is used for machine learning as we use today. I know that you mentioned Python several times in the presentations. Can you share your experience with machine learning for the first time?
Sure. So when I did machine learning before the current incarnation with TensorFlow and Python was way back in 1992. Is that right?
Ooh.
No, 1993, one of those years. And that was not really machine learning, that was AI. And this was before we had these modern algorithms to do the kind of things that we can do today. And it was using languages like Prolog or Lisp to do basic inference or basic logic inference. My experience with that was terrible because, at the time it was a very interesting thing to learn. I was part of a cohort in England that they were a little bit like you guys are doing, where it was to train the next generation of people to help industry. And they thought
Mm-hmm.
AI would be a big boost to industry back in 1992, which was amazing foresight on their part, but a little too early. But at that time, there was no way that you could deploy anything that you built in Prolog or Lisp. So it ended up being really useless. And that's why I'm particularly excited today about the fact that with things like TensorFlow, the models that you build, you've got places where you can deploy them. You can put it on the
Yes.
web, you can put it on mobile. It's all very nice to build a model, but if it's only on your machine, what use is it? So that was my experience back then. And I don't think it's a coincidence that the famous AI winter kind of
Mm-hmm.
started around then, because there were people doing AI, there were people who saw the opportunity around AI, including the UK government who brought me in to do that way back then. But the problem was the opportunity could not be hit because there was just no way that you could deploy your AI.
Can you share more about the first project that you were working on with machine learning?
The very first one way back then,
Yeah.
it was basic inference. So really being able to do logical connections between things. So for example, I don't know, you could say if person A is related to person B and person B is related to person C, is person A related to person C? To be able to, do that kind of very basic inference and have a computer
Mm-hmm.
start being able to understand those types of relationships, which is very primitive compared to the kind of things you can do today with like natural language processing and computer vision and all that kind of stuff. And it was really building algorithms and figuring out algorithms for complex relationships like that. As well as there was a language called Lisp, which stands for list processing. Still a very
Mm-hmm.
popular language today. But again, was it possible for us to build applications back then to maybe parse through text to understand sentiment in text? The answer was no. And but those were the kind of things that we were looking at way back then.
Oh, it's really interesting. Like, very the first like AI things that you make is like how to match people.
Yeah, not necessarily just people, but just any kind of relationship.
Mm.
So, like if company A is in the same business as company B and company B is in the same business as company C, or company A and C in the same business, to see like any of those kind of relationship dependency walking could be automated
Mm-hmm.
instead of like having people pouring through lots of data to be able to do it. That type of like relationship inference was the stuff that we were doing, but it was just way too early. It wasn't feasible.
Okay, that's really nice. Okay, and next questions. When I want to learn from journals, I usually find mathematical part of it hard to understand. Uh, how to be stronger so that I can understand this part of the journal, so the mathematical part of the journal, and also a few tricks will be nice. Can you share like the mathematical part of the journal, like how to make it easier to understand?
So I'm afraid I have bad news for you because I'm terrible at that part of it. I'm definitely. You say you want to move on from the "don't worry about it" part from Andrew M. Andrew and I are cut from the same mold when it comes to that because I'm very much about the application, and I don't really understand a lot of the more complex math, to be perfectly honest. And I tend to focus on the code.
Mm-hmm.
The one thing that I have asked Andrew about this, how can you be stronger and how can we encourage people to be more involved in the math? And in his teaching and in his courses, he definitely goes much deeper into the math than I do. But he only wants to go so deep as to help you to make an application out of it so that it's applicable rather than all of the underlying math theory. So I don't really have any tricks there other than, just becoming a stronger mathematician through study. But I'm not a very strong mathematician by any stretch of the imagination. Sorry. Sorry, it's not a great answer, Kenzie, but it's the best I got.
Thank you, Lawrence. Okay, next questions. It's quite long
Oh,
questions.
this is a long one, isn't it?
Yeah. Is there any ethical limitations to gather data to be used in machine learning?
So let's
Because there,
start with just that first part. If
yes.
there's any ethical limitations to gathering data, I think there are ethical considerations in everything that you do, not just in machine learning. So, gathering data, of course, is one part of it. So if you're gathering data from people, there are many things that you have to respect about the person that they may not want to share, and that's the clear low-hanging fruit when it comes to ethics. But I think there's also how you use the data is very, very important. So take, for example, I was using an example of the activity detection in my talk. And what if I had 1,000 people that I gathered data from to be able to build this model? But there were some people that I missed out. Maybe some people who have a particular, different ability. Maybe they can run faster than the rest of us. Maybe they can't walk. Who knows? And if, in my model, I start telling them that they're doing something that they're not, that can be quite offensive to them, particularly if it's when it comes to a disability. So not just gathering data with limitations, but also, how you use the data and how you use the model. And actually, a funny story about this is I'm not wearing it right now. I had to take it off, but I injured my hand over the weekend. If you follow me on Twitter, you see my hand with a bandage on it. And I use one of these mice, which is the Apple Magic Mouse. And the entire body of the Magic Mouse is a button. And it's smart enough to tell if I'm clicking with the left or clicking with the right or swiping or anything like that. But when I have a bandage on my hand, it can't tell. And so when I lost partial ability in this hand, my mouse suddenly became useless. So it's like, I had to take the bandage off to do this because I'm using my mouse in the presentation. The bandage is going back on when I'm finished. But again, it's a case of, when the model was built to determine how this works, they probably didn't take that into account. So again, we want to think about the people who are using your model. So consider the ethics of the data you gather for them, but also consider the ethics of how the model works for them, because it's really, really important for you to do that. And, the idea behind this is to build something that serves people, not, to build something that harms people. Okay, so the second part of the question is there might be cases where we want to make a better user experience by letting the program learn how users use the device, sample tracking web visits for ads, recording typing dictionary, eye tracking, scanning photo in a gallery, background listening, which might be understood by users who are eavesdropping and potentially risky if leaked outside the environment. Absolutely. So, the last part of it there, if leaked outside the environment, is it's not just that you have to be ethical in gathering the data, you also have to be ethical in how you store the data. And often, if you're using data to build a model, that you want to make sure that data is very protected. But the ultimate thing is if you're doing anything that has any kind of a user interface for humans, like the eye tracking and the stuff that you mentioned there, or scanning a photo, you really need as broad and diverse a data set as possible. You don't want to build something that doesn't recognize one color of eyes, for example. I actually have these funny genetics where my eyes change color in different heats. Sometimes I have blue eyes and sometimes I have green eyes. And I would love, if anybody's gathering any kind of data, to use my eyes as a measurement, because I'd love to see how systems will behave when the person's eyes change color. It's a very rare thing, and I have it. So it's what if you were building something that scanned a retina for logging in, and you trained, and I wanted to use it for me, but the day I have blue eyes, it doesn't work, and I can't log into my computer. So there's all of these kind of things when dealing with a person, that it's not as simple as grab data, build a model, and deploy it. That you really, really want to be careful in how you use that data and build it. So question, will this cause a problem between us and the users? If these are allowed, to what extent can we actually gather user data? Anything that you do in gathering data from users can potentially be a problem. So you have to be very careful about how you do it. You have to have a very clear contract about how you do it. And you also have to obey local laws about how you gather and store data. So, if these are allowed, to what extent can we actually gather user data? It's really down to that part of it is, what are you allowed to do by law? What are you allowed to do that the user gives you permission for? And are you going to do what you say you're going to do and not do other things? So, a lot of that is your decision. We try to give you the tools that will let you be effective at it, but ultimately ethics are your decision. I hope that answers the question.
Yes, I think it's answered the questions, because I saw the comment from Agung there.
Cool.
Next. How can machine learning and artificial intelligence stay in its main objective, that is helping mankind in every aspect of everything, and not replacing nor even make human capabilities worse?
Oh, great question. I'm going to focus on the word replacing that you put here. that there tends to be a lot of fear that solutions that are built with AI and ML will replace humans and replace human workers. There is no evidence of that. I'm beginning to think that's quite an irrational fear. Let me give an example of the doctors that I mentioned. Excuse me, the doctors that I mentioned earlier on with the diabetic retinopathy. This was a case of where there was a country where there was a massive shortage of ophthalmologists, and diabetic retinopathy, if not detected early, can lead to blindness. And there weren't enough doctors to be able to work with everybody, and a lot of people became blind who didn't need to become blind had they been treated early. But the AI didn't replace the doctors. The AI allowed the doctors to be able to scale and help more people. So that would be like number one, and that's like an AI thing. But if you remember at the beginning of my presentation, I went back and I spoke about the two other revolutions that are out there, the web revolution and the mobile one. The web one in particular, people said exactly the same thing. People said that, if you're able to do things on the web, if you're able to shop on the web, if you're able to, book a restaurant on the web, book travel on the web, then there's going to be masses and masses of unemployment. And that just didn't happen. If anything, the economy grew. Yes, employment did change, but the economy did grow. So let me talk about travel, for example. Once upon a time, I'm an old man now, but once upon a time when I was younger and I was at college, I went to college in one country and I lived in another. And then at the end of every semester, I'd have to book an airplane from where I was to where my family were. And the only way I could do that was I would have to take a bus into the city, and I would walk down the high street in the city and visit every travel agent. And at every travel agent, ask what their schedule was and ask what flights they had and ask how much it cost. It would be a day long for me to do that. And I would go and I would get all of these quotes and I would take a look at these quotes and I would say, I'm going to buy this ticket, and I would buy that ticket and then I would fly. And I could be sitting beside somebody who paid 5 times the amount. I could be sitting beside somebody who paid 1/5 of the amount. Nowadays that seems ridiculous because you can just open a browser and you can go to a travel site and you can book an air ticket. The people who worked in those shops were replaced. They're gone. That job is no longer around. Absolutely. But the travel industry grew. The cost of flying went down. The ability for the economy to grow because people were able to transport went up. And all of these new classes of jobs came about as a result. The expansion of the airline industry, the expansion of the web, even things like Uber for taking you to and from the airport and things like that all grew. So while sometimes there are some roles that will, be replaced by any kind of automation, like in my travel scenario, the result is always a net gain, and generally a massive net gain. So again, looking back at those charts that I showed at the beginning. So I think, when we're saying it's like staying this main objective and that's helping mankind, it can do that. I mean, it can be an economic boon to lift people out of poverty, as well as a boon in things like healthcare or crop disease and those kind of things that I was talking about. That's why I'm very, very excited about it. And, part of my job is to really educate people about what it is and not what it isn't, so that, we can all be motivated to go and build a better world for everybody else. And, part of that is building profitable businesses.
Awesome. I think if we discover a new technology, there will be another part of things that humans can contribute as well, right? Even
absolutely.
If they replace us. So yeah.
Yep.
Okay, next. Are there any topics that machine learning should not touch?
I think it would just be the same as any kind of technology work that you do. I'm not going to give you my personal ethics or my personal morals, but I want you to think about things that, for example, things that are illegal. You shouldn't be using machine learning to do things that are illegal in much the same way as you shouldn't be using traditional programming to do things that are illegal. And the different people in different countries have different moral standards and different political standards and those kind of things. Like whatever's appropriate for your area, whatever's inappropriate for your area, it's the same thing. We shouldn't be treating machine learning as something that's like different and exotic and new. It's just really, when it comes to things like this, we should be treating it just the same as anything else. So, if there's something that you wouldn't touch by writing traditional code, that would be my rule of thumb. Don't touch it with machine learning either.
Okay, that's a good tips. Next, what are your opinions on no-code machine learning platform?
I think they are a wonderful way to get started and a wonderful way to prototype. But I think ultimately you will still need to be able to do some coding, if nothing else, for tweaking and for optimizing models. Again, think about the similar paradigm for mobile app development or web app development. In the early days of both platforms, people were releasing no code solutions.
Mm-hmm.
Hey, build a website with drag and drop, build an iPhone application with drag and drop. But where the real business was and where the people drove the real innovation were the people who were still writing code. So no code machine learning platforms can give you a good start, but I really think you should be focused on code also.
Wait, the question is gone. Wait,
The question's
let me bring
gone.
it.
Is it
Let me
we're is
get
it
back.
I don't know if it's
Okay.
because we're out of time, or I can go a little longer if you need to.
Okay, let's answer Slido questions. Okay, my Slido is okay. Can you see the Slido?
I can't, sorry. Oh, something's changing. Okay, there we go. Let me see if I can make it bigger. It's a bit small. Boom.
Okay, let me.
Okay, it might be silly, but how do you learn math? I mean, as I answered earlier on, I'm a terrible mathematician. But how I learned math was at school and at college. And I think, that was my math learning path. When it comes to the machine learning stuff, definitely look at Andrew Ng's courses because, he covers the important math there. And if you don't understand that, at least he's covering it, and then you can go look it up elsewhere.
Sure.
So Naufal asked, would I mind to share my most challenging time in
Jay.
learning AI? Ooh, um, I think my most challenging time was when I started. The story behind this for me was how I started on TensorFlow.
Mm-hmm.
Was I got, must be 2.5 years ago, 3 years ago. A lot of people at Google were being trained in machine learning. And I was
Mm-hmm.
really excited to do it because, as I've shared earlier on, I had done AI and machine learning like 30 years ago, and it was a failure, but it was looking really exciting now. And I remember sitting in a classroom and I had sat through about 3 hours of calculus before I saw a single line of code. It was
Mm-hmm.
very hard to stay awake. And that was incredibly challenging for me. And that's when I began to realize that, hey, we should be on a journey to teach machine learning to developers using code as opposed to math. And, I actually brought that to the TensorFlow team at Google and said, we should be teaching it this way. And of course, their answer was, okay, you do it. And here I am. And so I think that was certainly the most challenging, as well as the story I shared, of course, back in the 1990s.
Yes.
So
Cool.
Celine asked if I don't mind share what my day-to-day is like as an AI lead at Google. Thanks in advance. No day is like any other, to be honest. It's every day is different, and that's one of the things I love most about it. In general, the work that I do falls into a few different buckets, so I could be doing
Mm-hmm.
any combination of these on any given day. One is managing a team of people who are developer advocates whose job it is to scale AI.
Mm-hmm.
One is, playing with the platform to try challenging new things. One of them is creating new teaching material. And one of them is just generally answering questions of people, both internal and external to Google, to help them understand. And then, of course, I do briefings like this one, and I do like some government briefings and university briefings and stuff like that. So there's no day is like any other, but ultimately we think about scalable developer advocacy as the bread and butter of what we do. And scalable developer advocacy is being able to speak with many people
Mm-hmm.
and to be able to kind of share broadly with many people. So making YouTube videos, speaking at conferences and things like that.
And I think regarding about the new materials, I think you just recently launched the version 2 of deep learning AI in the
Uh,
Coursera.
Yeah, actually, number three.
Oh, number 3.
So
Okay.
number three. So yeah, we just released TensorFlow Advanced Techniques, where we kind of go into two really exciting things for me. One is called the functional API. And
Mm-hmm.
if you're used to building simple models where it's like input and output, like I was showing earlier on, that solves a number of problems. But there are other problems that need to be served with much more complex and much more exotic models. For example, you've probably all seen object detection, where instead of just telling you what's in the picture, you also have bounding boxes showing where it is in the picture. That requires multiple outputs from a model, one output being this is what it is, and the other output being here's where the bounding box is. So that's a much more exotic type of model, and the functional API helps you do that. Things like optimizers, loss functions, layers, to be able to build your own, you can do that with the functional API. So that was pretty exciting. And then we also did some advanced computer vision. So we could really do things like interpreting how a computer sees. So when you show it a picture and it tells you it's a cat, it's like, well, how do you know? How do you see that that is a cat? So to learn about those kind of things. And that's the most recent specialization that we published.
Sure. I think I saw a chat on the YouTube comment. I would be happy if I can participate to documentations, translations. Is there a way that the students can help, like, to translate the
Yes,
documentations?
there is. I don't have the URL on hand right now. So maybe if they email you, February, I can follow up with you and you
Sure.
can send them the details. But yes, the community has been immensely helpful in translating the documentation, and we always want more help.
Sure. Okay, next questions. Maybe we can answer like 3 more questions, Laurence.
Sounds good.
In your opinion, is it machine learning in the future can be accessible to all people, even though they don't have any backgrounds in computer science?
So I would say yes, in a number of different ways. So the first way would be that, if you don't have a programming background, you're probably not going to be creating models, but there can be a huge economy built still around the creation of models and the applications that they run. There's product management, there's marketing, there's all of these other things that can happen that, as it becomes a bigger business, think about, if I go back to us talking about the app economy or the web economy, there are many, many people employed and involved in that who are not app developers or web developers. And I think, yes, it is accessible. But if you do want to build models, then there's the codeless. Somebody was asking about earlier on that there are tools that will allow you to do that, maybe at a prototyping level. And sometimes those tools are going to be enough. Sometimes those models are going to be enough, but often I think they won't be. But there will definitely be lots of options as the economy grows around ML and AI to be involved in that, even if you're not a programmer. But I would strongly recommend to learn Python. It's really easy. It is the easiest language to learn. And who knows, you might really become excited and become a TensorFlow developer and a model developer as a result.
Okay. Next, do you have any tips for us how to read, implement, and understanding machine learning paper, which sometimes full of math? I think we answered the full of math part. Maybe you can share a tips how to understanding machine learning paper better.
Yeah, the ones that I read and understand when I really don't want to go through the math are the ones that have some code. And so thankfully, many papers nowadays, they release some kind of code on GitHub. And so that's what I will generally do is I will take a quick read through the paper to understand what kind of things it's talking about. I will look at the diagrams to see how they design their algorithm. And then I'll dig into the code because I think I can understand the concepts easier through reading code than I can through reading math. I think there are many people who understand the concepts through reading math easier than through reading code. This is just me. So I think, if you're a coder, that would be the one thing is to look at those papers. And there's a website, I think it's called Papers with Code, that's really, really helpful for that.
Okay, thanks for the tips, Laurence. The last questions we had discussed much about TensorFlow in Python, but I am interested in TensorFlow in JS. Could you give us some sneak peek about that and how powerful it is?
Sure. TensorFlow.js is mind-blowing because it's JavaScript and you can train models in the browser using JavaScript. So if you have a GPU on your machine, it can actually use WebGL to access that GPU for training. That just blows my mind that, to me, JavaScript is like, it was invented to be this thing to make web pages a little bit more interactive. But now it's a full-blown language that can train neural networks, which I just think is amazing. So absolutely, yes, it's extremely powerful for you to be able to do that. But of course, being JavaScript, it can also be used on the back end with things like Node, so Node.js servers. So pretty much anything that you can do in TensorFlow, you can do in TensorFlow.js. If you look at some of the scenarios of what people have done, there's lots of amazing whizzy demos in the browser using media. One of the people on my team, Jason Mays, built a Harry Potter invisibility cloak where he can make himself vanish from a room on the webcam. It's really fun. Or lasers coming out of his eyes. But my personal favorite demo is, and if you go to youtube.com/TensorFlow, you can see all
Mm-hmm.
of these. Search for JavaScript show and tell, and you'll see them all. But my personal favorite demo was the famous painting, the Mona Lisa. There's a legend that as you walk around the art gallery, her eyes follow you. So
Oh,
somebody built a demo where using the webcam, it detects where you are in the frame. So if you move in the frame, like I'm moving now, not only will the Mona Lisa's eyes follow you, she will actually turn her head and follow you.
wow.
And it's really spooky and it's really cool. And to be able to, if I go back to what I was talking about earlier on code and the amount of code that you would have to write, that's really fun to get the Mona Lisa to do that. But if you had to write 100,000 lines of code to do it, you wouldn't do it. But if you can train a
Yeah.
machine learning model to say, well, I can detect where the person is in the frame, and I can detect as they move around the frame in maybe 10 lines of code, and then to use that model to then change the how the Mona Lisa looks at you, that gets really, really exciting and really fun.
Okay, that's about the questions. Last thing, Lawrence, because our students is right now will be starting their capstone project. Do you have any tips for them, like how to combining like Android, cloud computing that they already learned, as well as the machine learning part, so they can build like a impactful project after Bangkit?
Sure. Sure. So I think, many of the most impactful, simple projects, that don't take years of development have been in the computer vision space. Things like pretty much all of the ones I mentioned earlier on, like the crop disease and
Mm-hmm.
the diabetic retinopathy are computer vision. So I think if you want to build something that's impactful and you don't have a lot of time to do it, that's a really, really good place to get started. There's lots of data sets out there that you can start with and use. And so I'd say, that would be the first maybe to look at. If you're not interested in computer vision, then I would say maybe to think of something in the natural language processing space. And also the reason why I bring this up is that those are the two most in-demand skills by employers right now for machine learning engineers, people who know computer vision and people who can do natural language processing. So, think about those two spaces, look for open data sets that are out there. I'll share one amazing project that came from a group of students, and these were in India. And maybe something like this could be done for Indonesia. But
Mm-hmm.
India, as you know, has a pollution problem. And when you have pollution in the air, the only way that you'll get a measurement of the pollution in the air is from a weather station. But the weather station might be 20 miles from where you are, and you turn on the news and you see the pollution's at a certain value, but it could be far worse right outside your front door. And a
Mm-hmm.
lot of people who suffer from respiratory problems, are trusting a value of a measurement 20 miles away, that kind of thing. So what these students did was they tried an experiment where they got an air quality measure, and they took photographs of the sky. So they said, look, when the sky looks like this, the air quality is 85. When the sky looks like this, it's 87. So now all you have to do, because they trained that thing to match the sky picture to the label,
Mm-hmm.
and now when people use that app, you walk outside, you take a photograph of the sky, and it will give you an estimate of what it thinks the pollution is. And you don't need an air quality meter. So things like that, where it's using vision on a mobile device with a phone, because they all have a camera, you take a picture, you get an inference, was a very cool, very simple solution done using vision. And I'm sure there are millions of solutions like that out there for the people who have the imagination to think of them.
Wow, that's really cool. Like I never imagined like you can just like take a pictures and then train it using machine learning models, and it will
Yeah,
give you like the result of the air quality, basically.
yeah.
I
And
think
in
that's very
hindsight, yeah, in
yeah.
hindsight, when you think about it, it's obvious, right? Because the sky will be a different color based on the air quality, and it's
Yeah.
like you'll kind of like eyeball it and like say, okay, when it's like this, I'm not going out. But like a computer, when it's analyzing a photograph, it's probably much better at determining between different colors than you are and I am. So it's like, so now if you take a picture of the sky, it's probably better at judging the air quality than you and I would be. Not as good as an actual meter to read it, but if you don't have that meter, it's a really good solution. And it's your phone, right? Almost everybody
Yeah,
has one. So things
right.
like that are like I said, there's as many solutions out there as there are people to think them up. I never would have thought of that, and I'm really glad these students did.
Yes. Okay. We are running out of time. Thank you so much, Lawrence, for your time,
Thank
for
you.
your sharing. It's really inspiring. Like
Thank you.
the students really happy to be able like to communicate directly with you because before they just seeing you on the Coursera courses,
Yeah.
and this is their
Cool.
first time like meeting you in person for Bangkit.
Thank you. I'm sorry I can't be there physically in person. Maybe next year.
Yeah, we're happy to have you. Thank you so much, Lawrence, for your time.
Thank
Thank you,
you.
everyone, for
Take
joining
care.
us today. Yeah, have a great day and see you again. Bye.
Thank you. Bye.